In this lecture, we will explore the aha moments behind the DeepSeek R1 model. One of the main breakthroughs came from improving how transformers handle long texts. Traditional transformer models process every word in relation to every other word, which leads to an enormous computational cost. If you remember the attention mechanism we discussed earlier, it tries to find relationships among all words in a sentence, even when some are not relevant. DeepSeek introduced a smarter approach by focusing only on the most important words. This technique is called hierarchical attention. Instead of analyzing every single word connection, the model identifies which words carry the most meaning and focuses its attention there. For example, when humans read a paragraph, we do not process every single word in detail. We naturally scan and pick out the key terms to understand the main idea. DeepSeek applies this same principle computationally, allowing it to focus on essential words and ignore the rest. This concept also connects to sparse attention, where the model compares relationships only among critical tokens such as nouns and verbs, instead of analyzing all pairs of words. By doing this, it avoids wasting effort on less meaningful connections, reducing unnecessary computation. Another important concept introduced was hierarchical chunking. Instead of processing an entire long document at once, DeepSeek divides it into smaller, manageable sections. Each section is processed individually to capture its local meaning, and then the model combines these results to understand the global context. For example, imagine summarizing a 100-page novel. A traditional model would try to connect every word across all pages, resulting in millions of unnecessary comparisons. DeepSeek, however, splits the novel into chapters, analyzes each chapter separately, identifies the most meaningful sentences and words, and then merges the insights from all chapters. This approach significantly reduces computational effort by nearly 70%. While maintaining strong understanding and accuracy. The second major breakthrough was dynamic context gating. Traditional models sometimes get confused when users change their questions mid-conversation. For instance, if someone says, "I want to book a flight to Paris, wait, no, to Berlin," an older model might still try to process both destinations. DeepSeek, on the other hand, dynamically refocuses its attention based on the most recent context. It recognizes that the user has changed their mind and correctly responds about Berlin only. Dynamic context gating works by assigning different importance levels or weights to various parts of the input. It prioritizes the most recent and relevant information while downplaying older or less useful data. This makes the model more accurate and efficient, especially during interactive conversations. In summary, DeepSeek's key innovations, hierarchical attention, sparse attention, hierarchical chunking, and dynamic context gating, dramatically reduce computational cost while improving accuracy and contextual understanding. In the next lecture, we will discuss more reasons why DeepSeek R1 is not only highly efficient, but also remarkably cost-effective.